Hello friends, my name is Vivek Sharma. Today we can cover this interesting problem that's called cousins in binary tree. So we have been given a binary tree and we need to find two nodes of a binary tree that are cousins, and the property of the cousins is they should have the same depth and should have the different parents. Okay, so let's try to understand this problem from the whiteboard. So let's say we have been given this x value is 4 and 3. So x value is here 4, right? And by value is 3, right? So 4 is here and 3 is here. Okay, so what is the depth of 4? Right, so depth of 4 is 2, right? So 1 and 1 2. And what is the depth of 3? That is 1, right? So this depth is 2 and this depth is 1, so they are on the different depth, right? But as per the uh, property of cousins, the property of cousins is they should have the same depth but have the different parents, right? So the depth is different, so depth should be same, right? So we will return false here. It is not the, these both nodes are not the cousins. Okay, all right. So second is 5 and 4. So 5 and 4. Now let's see the depth. So here 1 and 2, 1 and 2. So depth is same, that is 2. What about the parent? So 4 parent is 2 and 5 parent is 3. So they have the different parent and the same depth, that is 2. So we should return true here. Now let's move on to the third example. So third example is given is 2 and 3. Okay. So 2 and 3, they are the nodes. So they have the same depth. That's nice. But the parent is same. So parent should be different, right? So in fact, we can note down the requirement: same depth, different parent. That's what exactly we need to do. Okay, if they have the same depth and different parent, then they are the cousins, otherwise they are not the cousins. All right, so how we are going to solve this problem? So what we will do, this is definitely because this is a binary tree, and we need to find the depth. So depth means basically, if we will start, for example, if we have to find the depth of let's say this node, right, 3 node, then we need to reach till 3, right? There is no way. I mean, if we will start from root, if we have to go to 3, we need to traverse this tree from top to bottom of approach, right? Top to bottom, top to down approach, right? Similarly, we have to find the 4, or we have to find the parent of 4 or the depth of the 4. Then we have to start, we have been given the root, right? So we have been given the root, that is 1. Then there is only way to go to 4 is following the top to down approach. What does that mean? In simple terms, like if this is a binary tree and if we have to come from top to down and we have to traverse like these nodes left and right, the most intuitive thing is the recursion, right? So what we will do, we will recursively go down, and sometimes without recursion also it works, but yeah, it depends upon the problem itself, like what kind of the problem we are going to solve. But in this particular problem, if we have to go to dev, then what we can do, we can go basically left and right manner, whatever we do in the recursion, right? General template. And once we will go into the recursion left and right child, then we can increment our depth as well. Let's say here the depth is 0, right? Once we will go to this level, then we will have the depth 1, right? And once we will go to this level, right? So these are the different levels. This is 0 level, this is first level, this is second level. So once we will move to different levels, we will keep increasing the depth, and this way we will have the depth for the given nodes. So now if we are having the depths and we can record the parent as well, then we can compare in the caller method. If the depth is same and the parent is different, then we can return, right? if if this condition is meeting, right, if the same depth and different parent, then we will return true, right? And if this condition is not meeting, right, if any of the conditions are not satisfied, then we will go ahead and return false, right? So this is a straightforward thing, the condition wise. Now the question arises here, how we are like now we are clear, right? So what we are going to do and how we are going to calculate the depth, but where, I mean, In terms of the traversal, once we will start from the root and we will just do the traversal of the tree, where we are going to store these depth and parent. So we need some structure. Either we can use some data structure, hash table kind of data structure, or we can create our own object, right? So that way it will be little bit convenient, right? Why convenient? So that at least we will have somewhere the parent node and the depth node for these nodes, and we can use those in the caller method to return the output, right? So once we will create a couple of placeholders, then I think the picture will be pretty much clear. So let's say we are having this placeholder, okay, class node. I'm creating another object class node here, and let's say this guy is having uh, two members here, okay. One is the parent and another is the depth, right? Because we need to make the decision based on the depth and the different parents, right? If the same depth and the different parents. And here the straightforward thing what we can do, we can similarly create another method that's called get node here, get node, okay. And here we can pass root null. So null is parent here because we need to uh, store this parent as well, right? And x, and here let's say pass new node, okay, so that we will fill this object and then we will return to node 1. Similarly, let's go ahead and do the node 2 for buy as well, okay. So root null, null is the parent right now because root's parent is null, right? And here buy, and similarly new node, okay. And in the end what we will return, if node 1 dot parent is not equal to node 2 dot parent, right? Node 2 dot parent, if the parent is different, and node 1 dot depth equals to node 2 dot depth, if depth is same and parent is different, then it will return true. And if any of the condition is not satisfied, then it will return false, right? Because we need to use the AND, because it's also using have the these tightly coupled, these both conditions should be satisfied if they're the same depth but have different parents, right? So same depth and different parents, so here basically we have to use AND, right? All right, so now we need to implement this method. And how we will implement this method, the similar way that we have seen in our whiteboard. So get node, what we will do here, tree node root, and this guy is parent, tree node is parent, okay. All right, and what is this, x, right? So int val we can say, or value, right? And this guy is node. All right, now first of all we need to write the base condition, because this is we will be going top to bottom, right? So we are planning to use the recursion here, right? So if root is null, then we are going ahead returning null, and get node we will call for the left side, right? And parent will be root in this case, val will be same, and node will also be same. Let's go ahead and call this for the right side as well, right? And in the end, because the return type is nodes, so we will return node. Now this node should be, we need to set these two parameters, parent and depth. So let's go ahead and set those. On what basis we will set those, right? So let's come here, right? So we started from 1, and then we will search this value 4, okay. We will go left, and then we will say, okay, 2 is equal to 4 or not. It's not equal to 4. Then let's say we again go to left, and then we will say, okay, 4 is equals to, so now this guy 4 is equal to the given value 4. Then we will set our parent, and that is 2. We are tracking that parent as well, and the depth as well, okay. So I think we did not introduce depth, so we need another parameter here, the depth as well, right? So we will set the depth as well, and the depth here it will be 0, and then we will keep incrementing depth as well at each iteration, at each level, okay. So that's what we need to do. So depth here, and initially it will be 0, so let's go ahead and pass 0 here, and depth plus 1, right? All right, okay. So what generally happens for the depth, we started from the root node. Let's consider, I'm just doing the control Z just to clear a couple of things here. So we started from root and depth is 0 here. We came here and then depth is 1. We come here, depth is 2, and then it will recurse back. So here is still uh, depth will be 2 for this particular node, but if it will come here, then it will come here, then again it will be 0, and 0 means the root depth will still be 0, right? So just remember, like, it's coming back to the recursion means the depth is basically it's not propagating this depth to the root, right? So each label is having the different root, different depth, because it's going to the implicit stack, right? Implicit stack means like first root depth is 0, then 1, then 2, and then 2 we are popping up from the recursion stack, and then 1 we are popping up, and then still root is still having 0, and then it will be pushing this depth, and that is 1, so it will be 1. So what I mean to say, each label is having the different depth, and the reason of because we are tracking that in the recursion on the implicit stack. So just wanted to clarify this. So as we have seen, like if this val equals to root dot val, then what we are going to do here, we will set our node dot parent equals to root. In fact, this is parent, right? So parent, we are having the separate variable, this parent, right? So if we are passing root dot left, then its parent will be root, right? So we are passing root dot left to our recursion, then this is the parent, right? So this is the parent and this is the root. Root dot left is becomes root, right? So root dot left we are passing to this, so this root dot left becomes root, and now the parent is this parent. So this is the parent, and root dot left we passed, and similarly root dot left we passed to the recursion, and then this root will become parent. Okay, so that's exactly what we are doing in the code. Similarly, node dot depth equals to depth here. So this depth we are assigning here. Okay, so each individual label basically will have the depth, but once we will find this particular 4, then we are assigning. So at this level the depth is 2 and the parent is 2, and similarly we will find 3. At this level parent is 1 and depth is 1, right? So this guy 4 is having basically parent is 2 and depth is 2. If we pair is like that, and here the 3 is depth is 1 and parent is 1, right? So this is parent and this is depth, parent depth, parent depth. Okay, so parent should be same, parent should be different, not same. Depth should be same, right? So depth is different, so it should return false. Okay, so that's pretty much it. Let's go ahead and compile this. Okay, so this is compiling, so looks like there is no syntax errors here. Complexity wise, because we are going ahead, uh, we are calling this method implementation, and we are calling, in the worst case it will be if it is the tree is like the linked list. Linked list means if it is a skewed tree, right? This tree can also happen like that. Okay, so this is called a skewed tree, or it is in the form of linked list, right? In that case basically it has to traverse each and every node. So time complexity in the worst case it will be order of n, and space complexity will also be order of n in that case, because in the this implicit stack, recursion stack, uh, in the worst case we will be storing each and every node in case the tree is really not balanced, or it is skewed, or it is unbalanced tree, or it is a skewed tree, right? So we are considering that worst case scenario as well. So let's go ahead and try to submit this if it works. So looks like this code is working fine. Just a very quick summary before ending this video. Here the main requirement is basically to have the same depth and the different parents. So we here the plus point is that we have been already been given these nodes x5 and by4, and we need to start our traversing from the root, right? So once we have to start from the root, we already know that we have to reach at this point. Then it is easier way basically to traverse from top to bottom, right? So use the recursion here, top to bottom. In the tree, like in most of the cases, like 70 to 80% cases, we use like top to bottom, and it's in the recursion. But it really depends, it's arguable, it's I cannot tell that it is 7 to 80%, but it is like in my view. But most of the tree template is like that only. Okay, so once we will start from the root and then we will go to the 5, then we have to traverse this tree, each node left and right side, and we have to reach to this 5, right? Somehow once we will reach to this 5, then we need two components, right? One is the parent and another is the depth, right? So depth we will find, and if we will start here, the depth is 0, then each traversal we will keep incrementing this depth. When I say each traversal, it means the each traversal of the each level, right? So each level we will keep increasing this depth. So till this node the depth has become 2, right? So we will assign depth, right, from our implementation, and we will keep a track of the parent as well. So we will assign the parent as well. So we will do like this: root and the parent, and this val is nothing but it is for the x node and this is for the y node. And once we will find our value, then we are storing this parent and depth, and in the caller method we are checking out, okay, it should be the different parent and the same depth. And if it is the case, then it will return true. If this is not the case, then it will return false. And here another thing is, we just defined this structure. We just took this structure for little bit more convenient. Another way is like might be like multiple ways. We can take another data structure like hash table kind of structure, or we can use without a structure with the global variable. So there are multiple ways, but this is like little bit cleaner and a little bit intuitive to solve this problem. So hopefully this might be useful. Thanks a lot. Have a good one. Bye.